Last time we met linear independence and span. Today we prove the linear dependence lemma. Because apparently every useful theorem begins as a suspiciously technical sentence. The lemma says that in a dependent list, one vector is redundant, and removing the right one does not change the span. Here is the lemma. Start with a linearly dependent list v1 through vm, and assume v1 is not 0. Then some vector vj, not the first one, can be written using earlier vectors. And if we remove that vj, the span of the whole list stays exactly the same. One vector was decorative. Very brave of it. To prove it, begin with what linear dependence means. Because the list is linearly dependent, there are scalars a1 through am, not all 0, that make this equation true. The scalars live in the field F, and the vectors live in the vector space V. Yes, we are stating the obvious. Because notation unsupervised is how disasters hatch. Now choose J to be the largest index whose coefficient is not 0. Largest means every coefficient after aj is 0, while aj itself is not 0. Also, j cannot be 1. If only a1 were non-zero, then a1 times v1 equals 0, forcing v1 to be 0, which is forbidden by the hypothesis. Since all later coefficients are 0, the dependence equation stops at vj. Because aj is not 0, we are allowed to divide by it. Finally, a coefficient earns its keep. This equation says vj is a linear combination of earlier vectors. That proves part A of the lemma. Now for part B. Why does removing vj leave the span unchanged? Any linear combination that used vj can replace vj with the formula we just found. So deleting vj does not delete any vector from the span. It only deletes the redundancy. A tiny act of algebraic housekeeping. Here is the entire lemma in a harmless example, before the notation starts wearing a cape. In R2, take v1 equals 1, 0, v2 equals 0, 1, and v3 equals 1, 1. The third vector is just the first plus the second. Equivalently, v1 plus v2 minus v3 equals 0, so the list is dependent. The lemma tells us to remove the redundant vector v3 and the span stays the same. This lemma is not just a cute trick. It is the tool that lets us compare spanning lists and linearly independent lists. Next, we will use this lemma to prove that a spanning list must be at least as long as any linearly independent list. Then we will prove that every finite-dimensional vector space has a basis, meaning a list that spans and is linearly independent. Finally, we will prove that all bases of the same finite-dimensional vector space have the same length. Only then do we earn the right to say dimension is well defined. Mathematics, where even counting needs a permit.